Hi. In the last video of this series, you saw that a complete toolchain is involved when you translate a simple Hello World program into an executable. And in the last video, the focus was mainly on this first tool of this toolchain, the preprocessor. Now, this video is about the other tools. So, what we know so far is that we can stop this toolchain after the preprocessor with this option -uppercase E, and then we see on the standard output by default the output, the result of the preprocessor. And for the Hello World program, this essentially meant that this include directive was replaced with this so-called declaration of the printf function. You know that this is not entirely true because we have this leftovers of the preprocessor with informations about the name of the source file. But it's good enough to continue from this point with the rest of the toolchain and just assume that this is what the next tool, the compiler, gets as input. You can stop the toolchain after the compiler generated some assembly code. I will show you that in the terminal, and I will play around with this assembly code and also show you how you can resume the toolchain with this assembly code. So if you use GCC together with an assembly file, then it automatically begins the toolchain with the assembler. So GCC assumes that this extension .s is only used for assembly code and not for C code. First, I want to point out again, if I want to use on my computer actually GCC, I have to use GCC-11. That's because I'm using Mac, thank you Apple, and this is the homebrew installation of GCC. So this might be different on your installation. You probably just have to use GCC without any other stuff. Now, if I use this option to generate assembly code, it generates me this file hello.s, lowercase s. And here you actually see quite a few things that are not so relevant. Actually, everything after this red instruction here. So I will just delete everything from this line to the end of the file. Boom, gone. Now, before I show you that this is still legal assembly code and that you still can translate it into an executable, let me show you a few things. You see here this so-called label main, or actually underscore main, and this is a label for the assembly instructions that are coming here. And this is the code the compiler generated from this function definition. What you also see is there is no label underscore printf or printf at all. So there is no code for this function printf. There is no way that later we could generate from this assembly code machine instructions for that. So these machine instructions have to come from somewhere else. You also might notice that we have here something which reads call underscore puts. And so this is actually kind of an optimization. The compiler knows about this function printf for some reason because it's part of the standard library and knows that in this case it can call a function with the same effect. So, but think of this as basically calling this function printf, which is nowhere implemented here. Now, to show you that I didn't delete anything of relevance, just change this here to an uppercase H, and then I will generate from this assembly code some executable. And I just resume the toolchain, beginning with this assembly code that I just modified. Now it runs through the rest of the toolchain and generates a.out. Just to prove that this a.out was really generated just a few moments ago and not somehow prepared. Let's change this here again. Let's also change this to an uppercase letter. And of course, you also should play around with these things. Next thing I can show you how to use the Ulm C compiler for generate. The next thing I want to show you here is how to use the Ulm C compiler for generating some assembly code for the Ulm. Basically the same thing, just change the name of the compiler, and then you see this assembly code looks different, but certain things are kind of similar. And of course here you also can play around. For example, change here this to hello, or now it's hello, and also resume the toolchain just by feeding UCC with hello.s. With the option -c, lowercase c, you can stop the toolchain after the assembler generated some machine code from the assembly code, a so-called object file. That's why by default you have this extension .o. And depending on the file extension, the toolchain begins with the preprocessor, runs through the compiler, runs through the assembler if you have a C file, and if you have an assembly code, it of course begins with the assembler. Now you also can resume the toolchain after the object file was generated, resuming it by using the linker or calling the linker with GCC. This is nice to use GCC as a wrapper in this respect and not directly call the linker, because then you don't have to care about the paths that are needed for finding the libraries that are required. Before I show you more about or give you more idea what the linker is doing, I first have to talk a bit about what is the content of these object files. You know that running an executable actually happens in two steps. First, the executable gets loaded into memory, or more precise, this text and data segment gets loaded, and the BSS segment gets zero initialized. And then after that, the sequential execution of instructions begins. Now, when you saw this assembly code for the Hello World program, you saw this label main followed by some assembly instructions. And from that, the assembler generates some machine code. So we have a sequence of machine instructions with a label main. And you saw there was no implementation for function printf. There was no label printf followed by some other assembly instructions. So this part is missing. We don't have an implementation for this function. And that means we have an incomplete text segment. The text segment is already using something, or is prepared to use something, which is not there yet. The linker later will fix this problem. The linker will add something to the text segment. It will add an implementation of function printf, and it also will fix this machine instructions for function main. I will not show you here the details how that's done. That's a topic of a different video. But I want to show you how to see on the command line what kind of symbols are used but undefined in an object file, and what kind of symbols or what kind of functions are available defined in this object file. So first I just generate this object file. And then with nm hello.o, you see that this symbol main is defined. The symbol puts is used but undefined. And you see that there are also certain other labels. But in general, what we will be interested in are always these symbols with a uppercase character up here. And then you see, for example, this is a symbol defined in the text segment. And you also, for example, see here an uppercase D if you have a global variable, unless you define it also as static. But these are details that are coming up. But in general, it means if you have here some uppercase U, it always means something is missing for getting executable. And this will be helpful later to understand why in larger projects where you have many source files, where some source file provides the implementation of something somewhere else is needed, the linker gives you an error because you get an error message like undefined references. Now, let me also show you how you actually see what this assembler is generating the machine code. You can use the command object dump with the options dash uppercase D, uppercase T, then feed it with hello.o. And then you see it's showing you basically here the instructions in hex representation, and here on the right hand side the assembly code from which it was generated. But actually it's a kind of disassembler where you see here these are the machine instructions, and here the reverse thing of the assembler happens. The object dump generates assembly code from given machine code. And let me also show you how you can see similar things with the Ulm C compiler. So I just stop here also after the object file was generated. And here I don't have a tool for showing the symbols, but you just can directly look into this object file, and it's a readable text file. So this is kind of a simplification for teaching purposes. And then you basically see the same thing. These are the instructions in the object file, and here on the right hand side the disassembled code. So basically the same thing. And this symbol table that you saw before with this command NM, you see basically here directly in the source file. So you also see that here the function printf is undefined, that the function main is defined also in the text segment, and you also see that we have other symbols. Lowercase always means it's for example here defined in the data segment but not visible to the linker. Some detail that I actually will explain in upcoming videos. Let me first create an object file with GCC from hello.c. And now I want to show you how to use GCC as a wrapper for invoking the linker, so that I can link this object file against the required library so that I get an executable. So that's basically it. Now I have this a.out. You also can use this option -v to see what this wrapper is actually doing. You see quite a few things, but if you look through this, you will see that it actually was just invoking the linker and not the whole toolchain. Another reason why we want to have our own compiler toolchain, if you use the Ulm C compiler first to generate this object file, and then use this option -v and feed this wrapper with the object file, and you see it's just invoking the Ulm linker. Or if you are not interested in these details, this is how you would directly link this object file against the Ulm standard libraries. And then again, you would have this executable. And in case of the Ulm executables, you also can look directly into the executable. And again, it's a readable text file, and you will see compared to the object file, it's a bit longer. You already saw how to link the object file with these libraries so that we finally get an executable, the Hello World program, that also contains this implementation of function printf. In the exercise, you will see some examples where we have, for example, more than just one C program, and then you also can observe here this toolchain that is involved, and we can use some nice example to make clear why we actually also need this preprocessor, and in particular this include guards. For example, in this case, you will see that you get an executable that just prints again hello world, and if you just make this minor modification, you also can compile it into an executable, but when you run it, it crashes and there will be no warning, and this is the motivation why we actually need this preprocessor and this include guards.